Greetings of the hour, guys. Hope all are fine. Today let's see one of the instrument in instrumental analysis, that is atomic absorption spectroscopy. So you are supposed to go through the instrumentation part and the theory part. So before moving on to the theory and instrumentation, let's make it very simple. Here we have atomic absorption. So the atoms should absorb the light radiation. Atom should absorb the light radiation, and the amount of light absorbed is measured as absorbance, that is atomic absorption spectroscopy. Let's go through the principle. Absorption of light by atomized metal when it is irradiated with electromagnetic radiation. Absorption of light by atomized metal when it is irradiated with electromagnetic radiation, that is atomic absorption spectroscopy. So the main application is to find out the metallic content in the sample. The application goes like this: determination of metallic content in the food industry, determination of calcium and magnesium in the blood serum, determination of lead in the petrol, etc. So let's go through the instrumentation part. This is hollow cathode lamp, and this is flame, this is monochromator, detector, and this is the readout instrument which shows the absorbance. Now let us dismantle the instrument. So let's divide into two parts, that is, one is hollow cathode lamp and the other one is flame. So first let us go through the hollow cathode lamp. This hollow cathode lamp consists of a cathode and an anode. So cathode, usually it is made up of a metal of interest. Metal of interest means, suppose if you want to estimate the sodium content in the sample, metal of interest, that is cathode, should be sodium. Cathode should be sodium. If you want to estimate calcium, cathode should be calcium. If you want to estimate copper, then cathode should be copper. Anode is made up of tungsten, and this chamber should be filled with inert gases. And when you pass a current between this cathode and anode, this inert gases undergoes ionization, and this ions of the inert gas hit the cathode, and metal will be converted into, that is, cathode will be converted into metal vapors, that is called as sputtering. Metal will be converted into metal vapors, that is called as sputtering, and that metal vapors will be converted into metal atoms. Metal vapors will be converted into metal atoms. So if you take sodium, sodium will be converted into sodium atoms. And that sodium atoms, let's go through this picture now. Sodium atom takes up energy. The red mark that shows it takes up energy, and it get excited to higher energy. We can see here this picture here. Metal atoms takes up energy and it get excited to higher energy. So at higher energy or at excited state, it is unstable. It always it wants to come back to the ground state. When it comes back to the ground state, it releases the characteristic radiation, that it releases the energy of 589 nanometer, wavelength of 589 nanometer. So this light will come out of the glass window. Hope you understand. So when you pass a current, inert ions of the inert gas undergo ionization. This ions hit the metal will be converted into metal vapor, that is called as sputtering, and metal in the metal vapor will be converted into metal atoms. Thus metal atoms takes up energy and it get excited. Under excited state, it is unstable, it always want to come back to the ground state. When it comes back to the ground state, it releases the light of characteristic wavelength, that is 589 wavelength of 589 nanometer, and this light will come out of the glass window. Let's go to the second part, that is flame. So if you want to estimate sodium, we have to take a solution of sodium chloride, and this sodium chloride, you know that sodium chloride, it will be in the form of ions in the solution, that is Na plus and Cl minus, and here there is nebulizer. Here you have to pass air, that is compressed air. The solution will be converted into droplets, that is solution will be converted into a mist. So this is stage 2. Here the heavier particle settles down, that is it drains out, and it is mixed with fuel in the mixing chamber, and this mist goes to the flame. When it goes to the flame, first thing is solvent evaporates, leaving behind solid. So solvent evaporates, leaving behind solid, and the solid vaporizes, leaving behind gaseous molecules, and this gaseous molecule will be converted into gaseous atoms. So sodium will be converted into sodium atoms. This sodium atoms get excited by absorbing the light of its own characteristic wavelength. Okay, so this one, remember, this one is excited, and the remaining one is unexcited metal atom, because it's very important to know the difference between excited and unexcited. This atomic absorption spectroscopy is concerned with unexcited metal atoms. In the previous slide, we have studied hollow cathode lamp and the stages in the flame separately. Now this is the whole setup of the instrument. What we have to do is we have to aspirate the sample into the flame, as we know, and it will be converted into a mist, and it is mixed with the fuel. Heavier particles settles down in the mixing chamber, and the other particles goes to the flame. In the flame, some of the metal atoms get excited by absorbing light, and some remain unexcited. So we are concerned with the unexcited metal atoms. This unexcited metal atoms takes up energy from the light radiation coming out of the hollow cathode lamp and get excited. It takes up light energy from the hollow cathode, energy coming out of the hollow cathode lamp, and it get excited. So we can see here, this is incident light, this is transmitted light. The amount of transmitted light has decreased because part of the light will be used up for the excitation from the ground state to excited state. Next, this transmitted light has to go through the monochromator. The role of monochromator is if it separates the light of different wavelength, because if now we are concerned with sodium, so we want only the absorbance of 589 nanometer. So monochromator separates the light of different wavelength, and it is passed through the, next it goes through the detector. Detectors convert the light signal into electrical signal, and it goes to the readout instrument. Here it is measured as absorbance. Okay, so it is understood that as the concentration of sodium increases, the absorbance increases, transmittance decreases. Let's go through the last slide, that is graphical part. It's called as calibration curve. It's a plot of absorbance versus concentration. That if you have taken sodium, that is absorbance versus concentration of sodium chloride, and this is, we can see here, this is, the concentration is 0. When the concentration is 0, when you aspirate it to the flame, there is no sodium content, there is no sodium atom in the flame, so all the light it is incident will be transmitted, so absorbance is 0. Next, let's go to the next concentration. It is 10 ppm. When you aspirate it to the flame, there will be sodium atoms, so part of the light will be used up, will be absorbed by the unexcited metal atoms, so it shows absorbance. Next concentration is 20, so the concentration is higher here, so the sodium atoms concentration will be also higher, so the concentration of sodium atoms will be higher, so more amount of light radiation will be absorbed, so the transmittance decreases, absorbance increases. Similarly, it goes for the next concentration. So this plot, it is called as calibration curve. Now this is, we know the concentration 10 ppm, 20 ppm, 30 ppm, but very important part is we have to we should know the concentration of the unknown sample. So here the concentration is not known to us. Okay, so you have to aspirate it to the flame. When you aspirate it to the flame, you get absorbance. So this absorbance, you have to plot it here, then you have to join the line to the curve, and you have to extrapolate it to the concentration. We get volume of the unknown sample. So concentration of sodium in the unknown sample. So hope you have understood atomic absorption spectroscopy. Thank you. Thanks for your time.